All right. Can everybody hear me there? Somebody say something in the chat if you can hear me. For some reason, I've lost the chat. I don't know where that's at. I have the participants over here. Oh, no. Oh, here's my chat button. Here we go. Can everybody hear me? How are you, Mr. Niazi? Doing good. Hello, hello, hello. You can hear? You can hear? Okay. So everyone can hear. All right. I fixed it to where there's no more waiting room. You guys can just come in and I don't have to let people in. So that's really good. That way I don't have to keep looking and clicking. All right. I do notice some people are not on mute. I don't hear any noises right now yet, but I'd have to ask you to not, well, maybe it's on my speaker's on. Yeah, my speaker's on, so oh yeah, no, everybody is on mute. Okay. Everybody's on mute. All right. That's good. I don't mind, once in a while if something really crazy is happening, for you to unmute and say something. But yeah, I'd rather not have everybody doing that at all. And the chat is sufficient. I have my eyes locked on the chat. For all intents and purposes, my interaction with you is me looking at that chat and seeing what you guys are saying. So without further ado, let's continue on with lecture. We have quite a bit of stuff to cover in a short amount of time, but I'm confident we can do it. Let me just extend this chat a little bit over here. That way we can make sure I'm hearing it. Gotta love this. Gotta love the ties. Yes, my wife got me this tie. It is the Mandelbrot set. It's a type of a fractal. The black regions are the set of all complex numbers such that under the fixed iterative map, f sub c of z is equal to z squared plus c does not exceed 2. So yeah, it's kind of cool. It generates this picture off of such a weird mathematical definition. You generate such a beautiful picture. Okay? So let's continue on our discussion here. Let me get my notes ready. First things first, is there any questions? What lesson are we going to go over first? We're going to cover the very last piece of 1.3. The very last piece of 1.3, and then move on to, here's our goal, 1.3, the last bit of it, 1.4, 1.5, 2.1, 2.2, 2.4. We're going to cover all of those today, all right? I just finished 2.2 today. Very good. So the last thing in 1.3 we didn't cover is the nth root, the principal nth root. Nth root of, let's say, some number a is equal to some number b, such that when I raise a b to the nth power, I get a. All right, so let's do some examples here. For example, the cube root of 8, this equals what? Well, using the fundamental theorem of arithmetic that all composite numbers break down. So 8 is really 2 times 4, and 4 is really 2 times 2. So notice that I have the cube root of 2 cubed. And the cube root of anything cubed is just, what was it? Cube, just 2. But here's where the principal nth root of an odd number and the principal nth root of an even number differ. Notice that, let's take the cube root of -8. And I know what you guys are thinking, oh, we can't take the square root of a negative number. Well, first things first, yes, you can take the square root of a negative number. Second thing, if you do take the square root of a negative number, you get an imaginary number, and we'll be covering that in 2.4, complex numbers. Third of all, matter of fact, you can take the cube root of a negative number, and here's why. Again, if we break this apart using the fundamental theorem of arithmetic, this breaks into the quantity -2 quantity cubed. So the cube root of -2 quantity cubed ends up becoming a -2. And here's why. This definition says the nth root of a is equal to b, and b is a number such that when I raise b to the nth power, we go back to a. So take a look. If the cube root of -8 is -2, then if I raise -2 to the third power, I better restore -8. So take a look, that does actually happen. -2 times a -2 times a -2, which becomes a 4 times a -2, which becomes an 8 minus 8. And can everybody see? Everybody can see, you can see. What is that thing from Cody? I don't know what that means. It's like a picture or something. I can't tell what that is. But anyways, good. Kiona, you can see. Brittany, you can see. Good, good. Yes, I appreciate the feedback. So if I ask a question and your hands aren't tied with like babies and drinks and whatnot, make sure to just say something. I would appreciate that. At least if several people say something, I know at least I'm talking to something, because I really don't hear or see you guys. So it's helpful for you to just respond via the chat. Okay, so now we've discussed the principal nth root, and we've kind of discussed the even and odd behavior. And so finally, I want to actually explicitly say what happens with even and odd behavior, where n is even versus n is odd. We notice that if I take the nth root of a is equal to b, and n is even, then the nth root of a is b and b only because of the principal part. But if there was no principal part, we get plus or minus, okay? The nth root of a is equal to b, and n is odd, though. We get nth root of a is equal to b, and b only. Even if it wasn't the principal, it's b only. So take a look. The cube root of -8 is -2 only. Even though the cube root of -8 is only -2, because only -2 is a number that when you cube it, it equals -8. Notice that +2, when you cube it, it does not equal -8, it equals +8. So the cube root of -8 is only -2. It cannot be +2. It has to be -2 and -2 only. Okay? So keep that in mind when we do problems and when you guys do homework and quizzes and tests. All right? Here's a little bit more off of 1.3. Here's the definition of a fractional power. Let's say I have x raised to the m over n power, okay? That's a fractional power. The power is a fraction. Well, this actually represents the nth root of x raised to the m power, okay? And this is always true. And you know, we can just talk about negative powers as well. Notice x to the negative m over n is the same thing as just 1 over x to the positive m over n. And that would just be this in the denominator. Okay? So, for example, if I had x to the negative 2/3, what does this mean? Well, this means it's 1 over x to the positive 2/3. What does that mean? Well, that means it's 1 over the square root. I'll put a 2 here, even though it's typically in the square root. We don't put the 2 there because it's implied. The square root of x to the 3rd power. So this entity goes to the power inside the radical, and this entity in the denominator tells you what root is it. Is it the m? It's the nth root. Nth root. So take a look. Here's another example. Y raised to the negative 44 over 7. Okay. Notice that this equals 1 over y to the positive 44 over 7. Notice that that reduces to 1 over the 7th roots of y to the 44th power. And we're just playing with this over and over again. Here's another example. Now let's use numbers. Let's say, what is 4 over 9 raised to the 2/3 power? Okay. Notice that this actually, what I meant was 3/2 power. Okay. What is it raised to the 3/2 power? Notice that the power distributes to the numerator and the denominator. Okay, and there's no negatives, so there's none of this flipping stuff. Okay. Next, we apply this definition to our right. This means this is the square root of 4 cubed divided by the square root of 9 cubed. Okay. Notice that this is really the square root of 4 squared times 4, and this is really the square root of 9 squared times the 9. All right. Once we represent it like that, we can easily distribute the radical to each terms, both in the numerator to both of the terms and to the denominator both of the terms. So I get this is the square root of 4 squared times square root of 4 divided by the square root of 9 squared times square root of 9. Notice that the square root of anything squared is just itself. So this reduces to 4 root 4 divided by 9 root 9. Okay? But there's more, right? Because 4 squared is really 2 and 9 squared is really 3. So this reduces to 4 times 2 divided by 9 times 3, which becomes 8 divided by 27. So 4 over 9 raised to the 3/2 power ends up equaling 8 over 27. Any questions? No. No, sir. All good. Not yet. Okay, I appreciate that feedback. So would it be root? So would it be root 4 squared times 9? I'm not sure exactly what you mean by that. Our initial starting point was we have the fraction 4/9 raised to the 3/2 power, to the 3/2 power. Then we distributed that power to the numerator and the denominator, and we applied this definition here. And then we just broke it apart and took the square roots, and we eventually ended up with 8/27. This part just shows you that the square root of 4 squared is just 4. This part shows you that the square root of 4 is just 2. Square root of 9 squared is 9, and the square root of 9 is 3. I hope that helps. How did you get the 9 at first on the numerator? There really is no 9 in the numerator. Maybe you think this looks like a 9, but this is a 4, and this is a 4, and they're being multiplied times each other, because 4 cubed is the same thing as 4 squared times 4. Does that answer your question, Luke? That's good, no problem. Ashley, did I answer your original question? Yes, okay, good. All right. Moving on to 1.4. Polynomials. A polynomial is an expression of the form a sub n x to the n plus a n minus 1 a n minus 1 x to the n minus 1 plus a1x plus a naught. So that means you move down the line. If we start at n is some number, we move down the line all the way until we don't have any powers for x. And over here, we subtracted from n each step 1 and 1 and 1, 1. Eventually, this got to x to the 1. And this last one, we have x to the 0, technically, because anything raised to the 0th power is 1. Okay? So, this term right here is called the leading coefficient. This term right here is called the constant term. Constant term. This number right here, if it's the largest number in our expression, is the degree of the polynomial. Okay? So 3 pieces of terminology having to do with polynomials. Okay? Now, one thing I will say, n must be, it has to be a positive integer. So that means x to the negative 2 plus x squared plus x cubed, this cannot be a polynomial because it has in it something to the negative power. Okay, so x to the negative 3 minus 2x squared minus 13x to the negative 17. This cannot be a polynomial because it has expressions that have negative exponents. Furthermore, obviously, x to the 3/4 plus 2x squared plus 9x minus 13. This can also not be a polynomial because this is not an integer. 3/4 is a rational number. They must be integers for this to hold, okay? They have to be integers. So these are examples that are not polynomials. Let's talk about examples that are polynomials. For example, negative 2x cubed plus 3x squared minus 5. This is a polynomial, okay? It has leading coefficient, which I'll call LC. Leading coefficient is equal to negative 2. It has a degree, which I'll call D, equal to 3. And it has a constant term, which I'll call CT, equal to negative 5, okay? So this is kind of like the anatomy of polynomials. Now we've talked about what is the anatomy of a polynomial. Now that we've discussed what is a polynomial and what is not a polynomial, let's do operations on the polynomials. Let's add, subtract, multiply these polynomials. Why don't we? Okay. So, for instance, here, let's take 3x to the 4th plus 2x cubed plus 13x plus 1. And let's add this to 2x to the 4th minus 3x cubed minus x plus 2. Whenever we add polynomials, you add like terms with like terms. Basically, it's like adding apples to apples and oranges to oranges, okay? If I come up and you have 2 apples and 2 oranges, and I come up and I give you 3 oranges, you still only have 2 apples. You may have more oranges now. You have 5 oranges, but you only have 2 apples. I can give you 1,000,000 oranges, you'll still only have 2 apples. So to increase or decrease the number of apples, you got to be either given or take apples. What do I mean by that? I mean things like x to the 4th power, it can only combine to another term that has x to the 4th power. 2x to the 3rd power, it can only combine with things that also has x to the 3rd power, okay? So notice that 3x to the 4th and 2x to the 4th, that means I have 5x to the 4th, or yes, 5x to the 4th. And so I cancel these terms out when I add them. Notice that this is a 2x cubed, this is a negative 3x cubed. So when I combine them, what's left is just a negative x cubed. Notice that here I have a 13x and a negative x. So when I add them, I get a 12x. Notice that I have a 1 here and a 2 here, so when I combine them, I get a 3. Here you go. That's it. So you got to get good at combining them. And it's really not that bad. I know what you're thinking. This has a 3 and this has a 3. Why don't I combine them? Don't they both have 3 in common? Well, no, we care about the x part. We only care about the x part. The only time we combine numbers is if they're just numbers with no x's in them, no variables in them. Now let's take those very 2 polynomials on our left, and instead of adding, let's subtract. So 3x to the 4th plus 2x cubed plus 13x plus 1. Let's get that. And let's, in this time, subtract it from 2x to the fourth minus 3x cubed minus x plus 2. Let's subtract them. Instead of adding them, let's subtract them. Now, here's a crucial step that most students tend to forget. So only if the powers are the same, you add together. Yes. Yes, only if the variable powers are the same, you combine them together. So here's a step where most students forget. You need to distribute this negative to each of these terms. It can't just go to this first one. It has to go to all of them. All right? So let me rewrite this part. 3x to the fourth plus 2x cubed plus 13x plus 1. Now, I'm going to replace that minus with a plus because that minus is now going to go hit each of these terms. When it hits this, this becomes a minus 2x to the fourth. When it hits this, this becomes a positive 3x to the third. When it hits this, it becomes positive x. And when it hits this, it becomes negative 2. Okay. So now that we've distributed the negative, we have to combine the like terms. Okay, so this 3x to the fourth and this negative 2x fourth, they combine to just give me x to the fourth, or 1x to the fourth. This 2x cubed and this 3x cubed combine to give me 5x cubed. So I'm going to cancel these out. This 13x and this positive 1x combine to give me a 14x. And this 1 and that negative 2 combine to give me a negative 1. Any questions so far? Let me know. I periodically look at the chat thing. No, sir. No, none. Okay, good. All right. Now, we added some, we subtracted some. Now let's try multiplying. Okay, let's do a simple case first. Let's get something like x squared and multiply it times, this is a monomial because it's one term. Let's multiply it by a binomial, which is two terms, something like 2x cubed minus 5x squared. All right. Notice that now this x squared has to distribute to both these terms, meaning this equals 2, or I can show you it get distributed. This becomes x squared, for instance, times 2x cubed minus x squared times 5x squared. From last class, when you have the same base is x, the exponents do what? The exponents add when you multiply with the same base. So then that reduces to 2x to the fifth. This 2 just comes along for the ride. Minus 5 just comes along for the ride. So 5 exponents add, so this becomes x to the fourth. So we just, for the first time, added, or we multiplied a monomial times a binomial. Now, let's do what you guys probably remember calling foiling and multiplying a binomial times a binomial. How about x plus 2 times 2x minus 3? Okay. This is what you guys typically call foiling, where you do first, outer, inner, last, okay? Let's do that. This is I don't like foiling, by the way. I don't like it being called foiling. I like it being called distribution, and you'll see why. But let's FOIL for one last time in our lives. So this is going to be 2x squared. We're going to call it FOIL for one last time in our lives. We will be distributing from now on. So this is 2x squared minus a 3x, and I'll show you what I mean. And then this becomes a 4x minus a 6. So once we've got done doing this part, we have to combine these like terms here. Okay? So I reproduce everything that doesn't have a like term, like this 2x squared. And these two like terms add up to give me just a positive x. And that minus 6 just comes along for the ride. So we're done. Okay. But notice, this result could have been achieved by doing it a different way. So I'll have an equal sign that goes in a different direction here. I could have said that this is the same thing as x times all of this, 2x minus 3, plus 2 times all of this, 2x minus 3. Okay? Notice that this is going to end up giving me the same thing as this in the box, and you'll see. Take a look. This equals 2x squared minus 3x plus 4x minus 6. All right? Notice when we combine these guys and we rewrite it, this is 2x squared plus x minus a 6. These are the same thing. Okay? This is called distribution. Doing it like this is distribution. And it is a superior method. And here's why. FOILing only works when you have a binomial, 2 terms, 1, 2, times another binomial, 2 terms, 1, 2. It doesn't work anymore if you multiply times a trinomial. And you're about to do that. So first, outer, inner, last doesn't work for a trinomial because it doesn't have just a first and an outer anymore. It has a beginning, a middle, an end. It's very different. So how about x plus 2 times 3x cubed plus 2x squared plus x. There is no first, outer, inner, last here. Can everybody see? Am I off camera? You can see. From my point of view, it looks like I'm off camera, but I'm really not. Okay. Yeah, I'm not off camera. Okay. Okay. Okay, so notice that we can distribute, meaning we fix one of them and multiply it times the whole thing on the right. Here we fixed x and multiply it times the whole thing on the right. Look. And then we added it to fixing 2, multiplying times everything on the right. Let's do the same thing here, because that's the only way we can do this. There is no foiling for this situation. This situation is impossible to foil. But you can distribute. So distribution can foil, but foil can't distribute, which makes distribution superior. So this is equal to x times everything here, 3x cubed plus 2x squared plus x. And then we got to add it to this 2 times this whole thing again, 3x cubed plus 2x squared plus x. All right. Now, all we got to do is send this term all the way through here, this x all the way to each of these terms, and this 2, send it through here to each of these terms. And what I mean by send it through, I mean multiply 2 times this, 2 times that, 2 times that. Multiply x times this, x times this, x times that. And then add it all up once you're done. So let's do it. This becomes 3x to the 4th plus 2x to the 3rd plus x squared plus 6x cubed plus 4x squared plus 2x. Okay? And now we just got to combine like terms. Do we have any x to the 4th powers? No, I only see 1, and that's this one. So it just comes along for the ride. It didn't combine with anything. What about x cubes? Do I have any x cubes? Yeah, I got some over here. I got some over here. I have 2 here and I have 6 here. 2 plus 6 is 8. So this becomes 8x cubed. All right. Do I have any squares? I got a square here. I got a square here. That means I combine that with that. This is a 1. This is a 4. 1 plus 4 is 5. So this is 5x squared. Got a 2x here. There's no x's. There's no other terms. I've crossed all the terms out. So that just comes along for the ride. Boom. Done. We multiplied a binomial. Yes, Carrie. Boom. Boom. Ah! Let me show you neck muscles. Ah, my collar doesn't let me shit. I was going to flex the neck, but my collar's up so you can't see it. Ah, you can't see it. This collar's all around my neck. Boom! All right. Now that we've multiplied a binomial times a trinomial, why don't we get crazy here? Why don't we get crazy? Let's do one example where we multiply a trinomial times a trinomial. And I'll need a lot of space for that. Don't worry. Everything I've recorded here will be on the internet. It'll be on YouTube and it'll be on Canvas. So even if you didn't write everything down, you'll be able to access it later. So how about we take x squared plus x plus 1 times 2x cubed minus 3x squared minus x plus 4. Wait, no, that's too many terms, right? So I'll just say plus 4 over here. I want 3 terms times 3 terms. Okay, so trinomial 1, 2, 3. Trinomial 1, 2, 3. Okay. So when we do trinomial times trinomial, you have to distribute 3 times because we fix our hand on the first term here, x squared, and we multiply it through all of this. 2x cubed minus 3x squared plus 4. Plus, now we move our finger from x squared to x. We put an x, and we multiply it times, you guessed it, all of this again. 2x cubed minus 3x squared plus 4. Now, shift our finger from x to 1, plus 1 times all of this. 2x cubed minus 3x squared plus 4. Told you we needed the whole board. Okay. Now, all I got to do is distribute this x squared, this x and this 1 to all of these and then regroup them. So let's go. This becomes 2x to the 5th minus 3x to the 4th plus 4x squared. This becomes 2x to the 4th minus 3x cubed plus 4x. This is just itself because anything times 1 is just itself. So now we have these 3 terms in the parentheses. Let's combine like terms. Is there any x to the 5ths? Nope. So I rewrite this term with the x to the 5th. 2x to the 5th. And I cross it out. Is there any x to the 4ths? I see one here, and I see one here, so I'll combine them. This is a negative 3, this is a 2, so this becomes a negative x to the 4th. Is there any x to the 3rds? I see an x to the 3rd here, I see an x to the 3rd here. This is a minus 3, this is a positive 2, so they combine to give me a negative x cubed. And I cancel them out. Is there any x squareds? This is an x squared. Oh, this is an x squared. Let's combine them. 4 and negative 3, that gives me a 1. So this becomes x squared. Goodbye. Goodbye. Is there any x terms? There's just one x term. There's a 4x right here, and I don't see any other x terms, so it just comes down for the ride, 4x. Goodbye. Is there any constant terms? Well, we've crossed out everything but this 4, and it just comes along for the ride. So this is what we get here. Any questions? Good. Do you guys see why distribution is superior to foiling now? Very good. Very good. It is way superior. So much easier. Yes, it is actually. Yeah, this whole first, outer, inner, last business doesn't work whenever you have these other cases. First, outer, inner, last only works with binomial times binomial. Where did you put the 2? Where did you put the 2 on the 2x to the 4th? Where did you put the 2 on the 2x to the 4th? Here? Because it had a 2 initially already, so when I multiply it by x, the x just ignores the 2. The 2 just comes along for the ride. The x only cares about the other x. And so they combine to become x to the 3 plus 1 power, which is the same thing as 4. Does that make sense, Sonia? Whenever we multiply through by that x, we don't get rid of the 2. It just comes along for the ride. It's just chilling. It's there, but it's not participating. If this x was if this x was a number like 5, then 2 would get involved. 2 would turn into 2 times 5 would turn into 10, and this x would then not be involved. But because this is at x times terms with x's in it, the 2 gets ignored. You don't have to put a 1 in front of an x. That is correct. You don't have to put a 1 in front of the x. And this negative 3 plus 2 equals 1. What is that about? Are you guys talking about this and that combining to give me negative? Yeah, there's a 1 here. This is technically a 1 here. We just don't put it there. There's technically a 1 here. We just don't put it there. There's technically a 1 here. We just don't put it there. Right? Is that what you guys mean? Yeah. Yes, sir. That's what she's talking about. Well, good. Good. All right. So we did a monomial times a binomial. We did a binomial times a binomial. We did a binomial times a trinomial. And we even messed around and went and did a trinomial times a trinomial. So that is a significant amount of multiplying these guys. Now let's do something called factoring, something that maybe you have been exposed to before, but you will not have mastered it on the level that you're about to master it with me. That's for sure. You're about to master factoring for sure. Okay. Of course, you can't just be sitting there drooling and hoping that you master it. You have to actually put in the work. But I'm going to try really hard to explain it in as many ways as possible and as clearly as possible so that the ball will be in your court and you'll be able to understand it if you practice it over and over again. Eventually, you'll understand it. But no, yeah, mathematics is not a spectator sport. Matter of fact, mathematics is not a sport at all. It is something on its own. It's called mathletics. And to get more mathletic, you have to do mathematics. To get more mathletic, to become a mathlete. So mathematics is like working out for your brain. It's really cool. Okay, so let's say I have x plus 1 times x plus 1. Matter of fact, let's just write it out like this. Let's say I have x plus 1 quantity squared, okay? Notice that this is the same thing as what I just erased, x plus 1 times itself. All right, notice that you could distribute and you get x times x plus 1 plus 1 times x plus 1, and you end up getting x squared plus x plus 1. Notice that when you combine like terms, this gives me x squared plus 2x plus 1, okay? Okay. Factoring. So we practiced just now how to multiply polynomials. This, from here all the way to here, was multiplication of polynomials. Factoring is going in the reverse. Meaning we start here, we are given this piece of information in polynomial form, and we figure out how can we express that as a product of two polynomials being multiplied by each other. So here's an example. X squared plus 7x plus 12. Factor this, meaning if we have this expression, notice that when we go back in time, it equaled something, in parentheses, multiplied by something else. How can we decompose this to something times something multiplied? Okay, that's what we want to do. That's what factoring is, okay? So here's a cool rule when you factor numbers. If the leading coefficient is equal to 1, so this has to be true. The leading coefficient out here has to equal 1. You can play this game. You need to come up with two numbers that when you add them, you get 7, and when you multiply them, you get 12. And this rule only works for when the leading coefficient is 1. So I'm going to set it up for you guys. I'm going to put an x here and an x here, but I'm going to have to add or subtract a number, here to somehow reproduce this x squared plus 7x plus 12. And it's going to be just like this. Here our number was 1 and 1, because notice 1 and 1, when you add them, you get a 2, and when you multiply them, you get a 1. So that's how you play this game. There is a 1 out here, so we played the game. What is two numbers that when we add them, we get 2, and when we multiply them, we get 1? That's 1 and 1. So what are two numbers that when you add them, you get 7, and when you multiply them, you get 12? 3 and 4. 3 and 4. And Sonia straight up did it. She wrote it. That's correct. And matter of fact, it's positive 3 and positive 4. Because look, when we distribute, we can check if we factored it right. Let's distribute this and see if we factored it right. All right, then we distribute, I get x squared plus 4x plus 3x plus 12. When we combine this term and that term, it becomes a 7x. And that is exactly this. So we did it right. This is the correct factorization for that polynomial. That's right. Very good. Let's do more examples. How about x squared plus 3x minus 10? What? So we look right here. Is this number out here a 1? Yes, it is, right? So we can play this game. What's two numbers that when we add them together, we get a 3, and when we multiply them together, we get a negative 10? 5 and negative 2. Excellent. Kiona. It's either Kiona. Yes. She's saying it's 5 and negative 2. So this is a positive 5. This is a negative 2. Let's check if Kiona's right. I think she is. Let's distribute and check. Okay, this equals x squared minus 2x. This equals 5x minus a 10. This becomes x squared plus 3x minus 10. Very good. Very good. Now, what about 5x squared plus 7x minus 6? What does this equal? Better yet, let me ask you, can we play the game we were playing before with this? No. I see someone saying no. Why not? No, they don't have anything in common. No, it's not a 1. That's it. No, it's not a 1. What's not the 1? It's this right here. This leading coefficient has to be a 1 for us to be able to play that game we were playing earlier. Now, when we play that game, it's not going to work. Okay? I'll prove it to you that it doesn't work. Pick two numbers that whenever you add them, you get a 7, and when you multiply them, you get a negative 6. Can you even think of one? Can you think of a pair of numbers that whenever you add them, you get a 7, positive 7, and when you multiply them, you get a negative 6? No. I see a no. I see some no's. Do I see any yeses? Can anybody come up with the number for me? I don't see any yeses, but I'm wondering if anybody thinks it's possible. So I'm guessing nobody thinks it's possible. Probably because I said right off the bat it's not, and I shouldn't have said that. I should have kept y'all guessing a little bit more. But yeah, you can't play that game. But you can play another game. And here's the new game. It's called factoring by grouping. What you do is you get the leading coefficient, 5, multiply it times the constant term, -6. Notice we end up with a -30 here, okay? Then you break down -30 to all of its possible factors. So -30 can equal -1 times 30. It can equal -2 times 15. It can equal -3 times 10, you know, all of these. There's more. I can think of some more. But notice the game is played by first multiplying the leading coefficient by the constant term to get this number. Then we want to find a pair of factors such that when we add the pair, they sum up to 7. So -1 plus 30, this equals -29. That doesn't work because it doesn't sum up to 7. -2 plus 15, yeah, that equals 13. That doesn't work. We're looking for them to add up to 7. -3 plus a 10, this one seems promising. -3 plus a 10, oh, cha-ching. That equals a 7. Okay, so that means this combination of a 3 and a 10 is what we need to do over here. Okay, so what do you guys think is the next logical step? Well, notice that 7x is the same thing as 10x minus 3x. This is the beautiful key step of factoring by grouping. That right there, what I circled, that is the beautiful key step of factoring by grouping. Because now I can change the 7x to what we have here. And it's going to do a lot for us. Okay? So I change the 7x to 10x minus 3x. And I keep this the same and that the same. I didn't change it. All right? This changes everything. Okay? Because notice that these two entities have something in common. They have a 5 in common. And notice that these two entities have something in common. They have a factor of 3 in common. Okay? So we're going to factor out those entities. So when I factor out a 5 from those terms, I get 5 times the quantity x squared plus 2x. Right? Because when I send that 5 back, this becomes 5x squared plus 10x. Now, when I factor out a 3, that becomes a -x minus a 2. Because when I send the 3 back in, I will get a -3x minus a 6. And so that's this right here. Okay? So we factored it appropriately. Now notice that these two have something else in common as well. They have an x in common. So I can pull that out as well. So I get 5x is equal to x plus 2. And this is just unchanged. Plus 3 -x minus 2. Okay? And notice that I can factor out a negative here. These two, I can pull out this negative and bring out here. So this becomes 5x times x plus 2 minus 3 times these have the positive signs now. X plus 2. Aha! Something beautiful just happened. Notice that now this term here and that term there have something in common. They have this quantity x plus 2 in common. So I can factor that whole thing out. Quantity x plus 2 can be factored out, and all that remains is what was here, a 5x, and what was here, a negative 3. Done. This is our fully factored initial expression. So I erased it, but we were supposed to factor this. Okay? So to prove that we indeed factored it correctly, let's distribute to see if we get this. Okay? When I distribute, I get x times 5x minus 3 plus 2 times 5x minus 3. Okay? This equals 5x squared minus 3x plus 2x minus 6. Oh, that's not a 2x, that should be a 10x. 2 times 5 is 10. Okay? And 2 times negative 3 is negative 6. Okay? So now notice that this breaks down to this. Because a negative 3 plus a positive 10 is, guess what? Why isn't x plus 2 quantity squared? Oh, so it's not squared, Ashley, because for x plus 2 quantity squared to occur, okay, that what you just said, for that to occur, this is what needs to happen. This needs to be multiplied by itself. Notice that right here, there's no multiplication. This is not being multiplied times itself. This is being multiplied by 5x. And this is being multiplied by a negative 3. So that's not occurring because they're not the same. But what we're doing is we're pulling out this x plus 2 coming here. And what remains is what used to be in front of the x plus 2s. Does it matter the order the x plus 2? No. No, Elijah. It doesn't. Quantity x plus 2 times quantity 5x minus 3 is the same thing as quantity 5x minus 3 times x plus 2. And I'll prove it. Or you can prove it to yourself by distributing. And we might as well do it real fast because it's good practice. Prove it to you. 5x times x plus 2 plus a negative 3 times x plus 2. This gives me 5x squared plus 10x minus 3x minus 6. So this becomes 5x squared plus 7x minus 6. Same as that. Okay, I see. Okay. Very good. I love to see my students understanding. It gets me really hyped. You're welcome, Elijah. Can we go over the grouping again? I was a little confused. Absolutely. We'll do more problems. I can officially say mind blown. Good. Math should be doing that. Here's another example. Let's do 2x squared plus 9x plus 9. Okay. Is this number out here a 1? No. So we can't do that original game. But we can do the factoring by grouping game. And that game is take the leading coefficient 2, multiply it by the constant term 9, get the result, which is 18. Then find the factors of 18 that sum up to equal this middle number 9. So 18 is the same thing as 18 times 1, and that's the same thing as 2 times 9, which is the same thing as, let's say, 6 times 3, right? But notice only the 6 times 3, only 6 plus 3 equals a 9. So what we're going to do is we're going to change 9x to 6x plus 3x. Because it's true, 9x is 6x plus 3x. Okay, we're not saying any, we're not telling a lie. 9x truly is 6x plus 3x. We're not playing any tricks. This is just a technique that's going to allow us to factor by grouping. Okay. Then we notice that these two guys have a 2x in common, and these two guys have a 3 in common. So I pull out a 2x out of these terms, a 2x, so that what I remain is I get an x here plus a 3, because 2x times 3 gives me 6x, and 2x times x gives me 2x squared. That's how you play this game here. You redistribute and see if you restored what you originally had. So this is factored appropriately. And then I pull out a 3 here, so this becomes x plus 3. This is correct because 3 times x gives me that 3x, and 3 times 9 gives me that 9. So these are factored appropriately. And now, factoring by grouping is beautiful because once you do this, you now have these guys in common. This quantity x plus 3 in common. So this equals quantity x plus 3 times what remains in front, this 2x and this positive 3. Done. We just factored by grouping again. Let me prove to you that we did it right by distributing and checking whether it equaled our original value here. Upon distribution, and I'll move the calculation up here, I get x times everything over here, 2x plus 3, plus 3 times everything over here, 2x plus 3. This equals 2x squared plus 3x plus 6x plus 9. And when we combine this 3x and that 6x, I get 2x squared plus 9x plus 9. Cha-chink. Cha-chink. Wow, this is so much easier. Jay, you have mathematicians to think. Better explain, I totally comprehended that. Yes. Of course you can comprehend that. Of course, anybody can comprehend mathematics. Let me ask everybody at home right now. Let me ask you a real legitimate question. Do you all have 2 eyes, 1 nose, 1 mouth, 1 head, 2 arms, 2 legs? If the answer to all those questions is yes, put a yes. If I mean, of course, some people have accidents and they get amputations. But what I'm trying to say is we're all born human beings, right? We all have 2 eyes, 1 nose, 2 legs. Yes. And guess what? The people who invented this stuff were human beings just like you. And the only difference was A, they were born before you even existed. And B, they worked really hard. They worked really hard every single day to discover this stuff. And it wasn't easy, and they got stuck, and some of them got stuck for hundreds of years. So, of course you can comprehend this stuff. Anyone can comprehend this stuff. If you are a human being, then you can comprehend mathematics, and you could become a mathematician. My high school and college teachers never taught it this way. Yeah, because they don't have the juice like that, Jay. And have a good teacher. I say that there are very few teachers out there who will do whatever it takes for their students. If that's what you call having a good teacher, then I aspire to be a good teacher for all of you, because I want to do whatever it takes to help you learn. And if that requires explaining it in 4 or 5 different ways, then I'll do it, because that's what I had to do for myself, for me to understand. I I was born. I didn't go to a fancy school. I wasn't born into a wealthy family. I didn't have access to tutors. That stuff was very expensive. So I had to teach myself. But one thing that I did have was a positive attitude, a mentality that anything is achievable through hard work and dedication, and tenacity, never giving up, no matter what. And that's easier said than done, but you just got to never give up. Never give up. Never give up. Keep trying, keep working. Eventually, you will get what you want. You will achieve your goals, whether that's in math class or in life or anything like that. Man, no kid, we really appreciate you big time. Yes, I appreciate all of y'all as well. I appreciate all of y'all. I want to be a positive influence on you and make you believe that not only is mathematics accessible to you, but that it's beautiful and it's something that maybe you should pursue. Okay? Appreciate all of y'all as well. Back when I was a student, I didn't. I had a lot of questions, and my teachers would tell me to shut up. I would ask them to prove things to me. You know, why is this the way it is? Can you explain? Why is the area of a triangle 1/2 base times height? Where did that come from? Are you just making that up? Why is that the formula? Provide justification. And I wouldn't get the justification. And that would make me very angry, because I didn't want to just take the teacher's word for it. I wanted proof. I'm not going to listen to them just because they say so. And you shouldn't listen to me just because I say so. You should use your brain and only accept what makes logical sense to you. And that should be accepted through rigorous thinking, through deductive reasoning and critical thinking, through justification, as we have right here. Okay? So, moving on, let's see where we're at here. Okay, flip through the text here. Now we're moving on to section 1.5. Factoring. Oh, wait, we've already been doing factoring. So we've been in 1.5. 1.5 is about factoring. So, see here. We did trinomials, we did binomials. Let's do some difference of squares. Let's do some difference of squares. All right. Let's factor 9x squared minus 25. Okay. So notice that not only is this not a 1, that we don't even have that middle term to play the factoring by grouping game. So this is a different situation than we've been dealing with altogether. But what we can notice is a trend here, because 9 is really 3 squared times x squared, and 25 is really 5 squared, right? So our equation over here is the same thing as 3 squared times x squared minus 5 squared. Notice that just like how in general, if x times y raised to the p power is the same thing as x to the p times y to the p, we can actually go in reverse. Some base to a power with another base to another power can go in reverse to this. I say that because look, we're given in this situation right here. So this can be as 3x times quantity squared minus 5 squared. We can represent this 3 squared times x squared like that. Okay, what does that buy us? Well, it kind of allows us to see that this is squared, and that there's no middle term. So why don't we factor it like 3x minus 5 times 3x plus 5. And I say this plus minus 5 thing here because I know once these two multiply times each other, I need to eventually get a negative 25. And they must have different signs for that negative to appear in front of the 25, right? And this 3x appeared because I know that I need a 3x quantity squared term. So once this 3x is multiplied by this 3x, I get this 3x quantity term. And I know what you're wondering. Well, usually when we do it, when we distribute, there's like 1, 2, 3, 4 terms that result. So this only has 2 terms. What's going to happen? Well, you'll see. Notice when we distribute, we get 3x times 3x plus 5 plus a negative 5 times 3x plus 5. This is a negative 5. Okay. So notice that when I distribute these through, I'm going to work up now. This becomes 3x times 3x is 3x quantity squared. It's self-squared. And then 3x times 5 becomes 15x. And then negative 5 times 3x becomes negative 15x. And negative 5 times positive 5 becomes a negative 25. Well, there's 4 terms there. There's only 2 terms here. What gives, huh? What gives? Did I mess up? Professor Niazi, you messed up. All that inspirational talk about you can achieve anything you set your mind to. Looks like you couldn't achieve this simple calculation, right? Oh, but let's see what Joseph has to say. 15 cancels out. Precisely correct, Joseph. And I know what you meant. You meant 15x cancels out. 15x cancels out with 15x. So then you get this 3x quantity squared minus this 25, which is the same thing as 5 squared, which this stuff is the same thing as this stuff, which was the same thing as this stuff, which was the same thing as this stuff. So we factored it. So that's a process called factoring by factoring a difference of squares. We notice that this is a difference of squares. This whole thing is something squared. It's 3 times x quantity squared. And this whole thing is something squared. It's 5 squared. And so we can do this process over and over again. Let's do it to a different example. How about 4x squared minus 36? Okay, again, notice that this breaks down to 2 squared times x squared minus 6 squared. Okay, And then we can rewrite that using this rule that we learned last class. This is 2 times x quantity squared minus 6 squared. Then we realize that if I write this out like this, 2x minus 6 times 2x plus 6, when this is minus, this is plus, we get that negative 36 we were craving to solve the problem. Furthermore, just like last time, the middle terms will cancel out. So let's not just take my word for it. You shouldn't take anyone's word for anything. You should go see for yourself. So let's see for ourselves here by distributing. So now I get 2x times 2x plus 6 plus this negative 6 times 2x plus 6. When I distribute it through, I get 4x squared, or, our 2x quantity squared, same thing, plus 12x minus 12x minus 36. 12x, negative 12x, cancel. So this equals 2x quantity squared minus 6 squared, which is the same thing as 4x squared minus 36. Same. Good question, Jay. Then you can't do this process. This process is only achievable when it's a difference of perfect squares. Let me show you something in general. If I have a plus b quantity cubed, how would I factor that? There's a general way to factor this, and you just get a plus b times a squared minus 2ab times plus b squared. Oh, there need not be a 2 here. It's just minus ab plus minus ab plus b squared. There we go. So what do I mean by that? I mean, let's say I had x plus 1 quantity cubed, okay? That means this should equal x plus 1 times x squared minus x times 1, which is x, plus 1 squared, which is 1. Let's see if this holds true once we distribute. Notice that this gives me x times x squared minus x plus 1 plus 1 times x squared minus x plus 1. Notice that bringing the calculation to the left-hand side. I get this is x cubed minus x squared plus x squared minus x plus 1. X's cancel out. X squareds cancel out. I'm left with x cubed plus 1. Okay? Does x cubed plus 1 indeed equal x plus 1 cubed? Well, x plus 1 cubed is this. So we should get, this is x squared plus 2x plus 1 times our x plus 1. Then this becomes x times x squared plus 2x plus 1 plus 1 times x squared plus 2x plus 1. This equals x cubed plus 2x squared plus x plus x squared plus 2x plus 1. Wait a second here. Oh, a cubed plus b cubed. Oh, wait a second. Something's going wrong here. So over here, when I wrote this is not necessarily true here. I read the screen wrong. I'm reading split screen right now, so I read the screen wrong, guys. So this is actually wrong. It's really a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared, okay? So let me reinvent a new example here. I saw the formula wrong, and clearly it's not working out, as you saw. So take a look. Let's show you an example. Let's do x cubed plus 2 cubed, all right? This is the same thing as x cubed plus 8, all right? So you'll usually be given something like x cubed plus 8. You'll have to notice that 8 is really 2 cubed. Then you'll have to know that I could break it down like this, where x is a and b is 2. This becomes x plus 2 times x squared minus 2 times x plus 2 squared, which is 4. Notice that this breaks down to, if I change this to a 4, or it's a 4, I can distribute and I get x times x squared minus 2x plus 4 plus 2 times x squared minus 2x plus 4. Then this equals x cubed minus 2x squared plus 4x plus 2x cubed minus 2x squared plus 4. Oh, wait. So this is the completion of this term. This becomes 2x cubed minus 4x plus 8. There we go. So now 2x here, AB, so this becomes x2, x squared minus 2x, 2 squared. So I do this here. This is a 4, 2 here. This is a that. So I distribute this as an x cubed minus 2x squared plus 4x plus 2x. This should be an x squared, not an x cubed. Okay, 2x squared minus 4x plus 8. Okay, that was the issue. Because now look, these 2x squared and this 2x squared can cancel. And this 4x squared and this 4x can cancel. And all that remains is this x cubed plus 8. So this indeed factored it appropriately. What happens when it's not a perfect square? That was your old question. There hasn't been any new questions. Okay. So if you ever are asked to factor something like this, you need to pick out if this number is a cube. So I'll show you a different example. This is the thing that you need to master. I wouldn't tell you to memorize it. I would tell you to just understand it. Okay? But yeah, that's what you need to master. Let me show you another example of that real quick before I have to move on. For instance, let's say you are given x cubed plus 27. Okay? You have to know, and they tell you factor this. Okay, you're commanded to factor. Well, you need to realize that this is x cubed plus 3 cubed. Okay, then you can use this method by saying, oh, this is x plus 3 quantity times x squared minus x times 3, which is 3x, plus 3 squared, which is 9. Okay? You'll notice that when I distribute, that this will restore my x cubed plus 27. This is x times x squared minus 3x plus 9, plus 3 times x squared minus 3x plus 9. Notice that this equals x cubed minus 3x squared plus 9x plus 3x squared minus 9x plus 27. Okay. That's just some chalk that didn't get erased. Now we cancel out terms. Notice this term, this negative 3x squared, and this positive 3x squared cancel. This negative 9x and this positive 9x cancel. So all that's left is x cubed plus 27. So we factored it appropriately right here. So this is just a technique for factoring a special case where you have the addition of two cubes. It's called the sum of cubes. And furthermore, you can also do a difference of two cubes. The equation for a difference of two cubes is as follows. And all of this stuff will be on the recording. Furthermore, all of this stuff is in your book as well. So if you don't get it with what I'm saying, you have the opportunity of looking at it in your book. This difference of cubes is as follows. A cubed minus b cubed is quantity a minus b times quantity a squared plus ab plus b squared. Okay, so here's an example. Let's say you're given x cubed minus 8. Okay, we notice that 8 is really 2 cubed. All right, then we know that that rule up there allows us to factor this. This rule tells us right here how to factor a difference of cubes. So this should be x minus 2 times x squared plus 2x plus 4. Because that's where that 2 squared. B is 2, so it's 2 squared is 4. Notice that when I distribute, I get x times x squared plus 2x plus 4 plus a negative 2 times x squared plus 2x plus 4. This breaks down to x cubed plus 2x plus x cubed plus 2x squared plus 4x minus 2x squared minus 4x minus 8. And so notice that the negative 2x squared and negative 2x squared cancels. The 4x squared and the negative 4x squared cancels. So all that remains is this x cubed minus 8. So we factored it appropriately using the difference of cubes. There really isn't much to this stuff. It's just a technique. You need to, I wouldn't say memorize it, but know that if you have a difference of cubes, this formula will appropriately factor it as a binomial times a trinomial. And this formula will do it for you for the sum of two cubes. All right, let's do some different kinds of factoring here. Let's do fractional factoring. Let's do something like this. 3x times the quantity x plus 2 raised to the negative 1/3 power plus 4 times x times 2. 4 times x plus 2 raised to the 2/3 power. What if you are asked to factor this? It seems kind of intimidating at first, doesn't it? Well, it's really not that bad, okay? What we want to do is make sure that these powers are the same. Because if these powers become the same, I could factor out this x plus 2 and this x plus 2. Right now, they're not the same. And the only way to make them the same is through some mathematical trickery, okay? Here's the mathematical trickery I'm talking about. Notice that negative 1/3 is the same thing as 3/3 minus 4/3, is it not? Who agrees? Negative 1/3 is the same thing as 3/3 minus 4/3. Who agrees? Some people agree. 2 people agree. I need more people. 3 people. I need more people than that. Who else agrees? Agreed. Okay. I see some agrees. I see some agrees. Maybe. What? Why maybe? Why maybe? Fractions are hard. Okay. I'm not great at fractions. Time to take a mathematical tangent and talk about some fractions. I will conceptually explain to you guys everything you need to know about fractions using a tasty analogy having to do with pizza. Yeah, pizza. Okay? All right. Let's say Professor Niazi has a cheese pizza, and let's say you guys have a pepperoni pizza. Okay? Imagine, yeah, you just ate pizza. Good for you. Imagine a scenario where we both have pizzas. You have pepperoni, I have cheese. Okay? So let's say my pizza is cut in half. So there's 2 slices in my pizza. And let's say your pizza is cut into fourths. So you have 4 slices in your total pizza. Okay? Let's say I'm getting a hankering for some of that yummy pepperoni. And I want to trade slices with you. Should I trade slices with you given this situation? Who thinks yes? And who thinks no? Someone vehemently said no. That's a capital no. That's a capital N-O. Someone said yes. Goodness. Okay. Joseph, we're going to change your mind here in a little bit. Okay. Here's why. I'm not going to trade my pizza with you. I would be giving up half my pizza for just a fourth of your pizza. Notice how big this dang slice is versus one of these slices. That's not a fair trade. I mean, if you like pepperoni better, no. We want to have an equal trade, an equal amount of pizza trade. It's not about preference and that. It's about, am I getting as much pizza as you're getting? Is this a fair trade? And actually, it's not. You got me. I misunderstood. Oh, it's okay, man. Don't worry about it. So this whole thing is to help you guys understand fractions, all right? I can't give you half of my pizza to get a fourth of your pizza. That's exactly why you can't add 1/2 and 1/4. You can't add them. You can't add 1/2 and 1/4. Okay? You're always taught that if you want to add fractions and they have different denominators, you have to make them get a common denominator, right? So the way I can add 1/2 to 1/4 is if I multiply top and bottom here by a fancy number 1. And the fancy number 1 has to be such a number 1 that it makes this denominator turn into a 4. So what number can I multiply 2 to make it turn into a 4? 2, 2, 2, 2, 2. So, okay, so I can't just multiply this by 2 and forget to do it to the top, okay? I have to multiply top and bottom by 2. Notice what happens here. 2 over 2, which is 1. I'm not changing anything. So this equals that, right? So whenever you multiply 2 over 2 times this fraction changes to 2 over 4 plus 1 over 4, right? Right? Good. So now that we have a common denominator 4, we can add the numerators. I can add 2 plus 1 to give me 3. So this becomes 3 over 4. Notice that converting this 2 to a 4 is the same thing as me pulling out a sword and cutting my pizza like this. It used to be cut in half, 1/2 here, 1/2 here, but now it's cut into fourths. Now, you best believe it, I will trade a pizza slice with you because it's a fair trade. Now I get just as much pizza as I gave. So it's a fair trade in that case. Does that make sense? That's why you have to get a common denominator when you add fractions. Because of pizza. All right, that makes sense. Very good. It's because of pizza. You have to get the common denominator or else you don't get a good pizza deal. So over here, we figured this out because this is the same thing as this. 3 minus 4 all over 3. Okay? So hopefully that helps you understand fractions more. Also, here's another example of fractions. Let's say I have 1 over 3 plus 1 over 4. I can't add these guys either. They have to have a common denominator. The standard practice is, we got this fraction, right? We look at the other denominator. We see what number is in the denominator. It's a 4. So we multiply top and bottom here by a fancy number 1, 4 over 4. Then we look at this guy. We look at its denominator. It's a 3. Then we multiply the opposite denominator, top and bottom, by 3 over 3. When you multiply fractions, the numerator is multiplied times the numerator. The denominator is multiplied times the denominator. So I get 4 all over 12 plus 3 all over 12. Okay? So now they have a common denominator. I can add the numerators. Yeah. Whenever you have a common denominator, you can add the numerators. And you can actually combine the numerator under one big denominator. It's just shorthand. So then this becomes 7 over 12. So adding fractions it's just like that. That's all you got to do in every case. Sometimes it'll be more complicated. It won't just be as simple as 1/3 plus 1/4. You might have some x's, some x squareds, but it's really the same concept. Look at 1, look at the opposite denominator, multiply top and bottom by that thing. Then look at this one,
look at the opposite denominator, multiply top and bottom by that thing. Once you multiply numerator times numerator, denominator times denominator, add the like terms in the numerator once you have a common denominator, that's it. Okay? Easy as that. Easy as eating pizza. So, trying to factor this guy, right? Notice that this ends up becoming the same thing as 3 over 3 minus 4 over 3. And I'll just rewrite this entity right here. All right. Notice that 3 over 3 is the same thing as 1. Okay? Notice after that what I can do here. Pretty cool. Nice. Good. Notice, I'm going to bring the calculation over here. Actually, let's recall something from the past. Recall. X to the m times x to the n is equal to the x to the m plus n. Okay? So by that rule, x plus 2 to the 1 minus 4/3 is the same thing as x plus 2 raised to the first power multiplied times x plus 2 raised to the negative 4/3 power. By that same rule. So I can decompose this to that, and this, I don't even have to put this 1, it's just implied. Okay, so this becomes, I'll bring this over here, this becomes 3x times x plus 2 times x plus 2 raised to the negative 4/3 plus 4 times x plus 2 raised to the 2/3 Oh, you see, I need to make it, I need to have something I can pull out here. All right. I need to have something I can pull out here. So now we have to discuss what is 2/3 in terms of this right here. So notice that 2/3 is the same thing as 3 over 3 minus 1 over 3, right? So applying the same logic, I can replace this 2/3 by 3 over 3 minus 1 over 3. And that's the same thing as 1 over 3. So that means this becomes 3x times x plus 2 times x plus 2 raised to the negative 4/3 plus 4 times x plus 2 raised to the 1 minus 1/3. Then applying this rule again to this piece, this becomes 3x times x plus 2 times x plus 2 raised to the negative 4/3 plus 4 times x plus 2 to the 1 times x plus 2 to the negative 1/3. And that 1 is there, it's implied, we can remove it. All this work because I wanted to get something to pull out. This is an x plus 2 to the 1. This is an x plus 2 to the 1. Now I can pull it out. So pulling it out gives me x plus 2 times what's remaining. This 3x times this x plus 2 to the negative 4/3 plus this 4 times this x plus 2 raised to the negative 1/3. Okay? Then you can also realize another thing. -4/3 is the same thing as -1/3 minus 3/3. So I can find a negative x plus 2 to the -1/3 as well. So this becomes x plus 2 times 3x times x plus 2 raised to the -1/3 minus 3/3, which is just like 1, plus 4 times x plus 2 raised to the -1/3, which means now I can factor out. Well, before I do that, so nobody gets confused, I'll write it out explicitly here.
Professor,
Yes.
I think we're all very confused right now.
Who's talking? Oh, okay. It's funny how you guys hack the system sometimes when my back is turned for too long. You're confused. Okay. A lot of people are confused. Too late. Me too. I haven't even been reading these. So you're putting a 2 and a 3. Wow. I have to scroll up to see stuff. Oof, I'm lost. Lost 2. Where are you putting the 3 in the numerators? 2/3. Why are you adding another x plus 1, x plus 2? So let me take a look at these guys. All right.
How about I explain it in a different way? Who was it that was talking to me?
Who was it that was talking to me? Sonia. Okay.
Thank you for letting me know, Sonia. All right. I'm just going to rewrite the original problem. I'm going to do less confusion here. X plus 2 raised
To the -1/3.
plus 4 times x plus 2 raised to the, what did it say?
2/3.
Positive 2/3. Okay. So notice that 2/3 plus some unknown number can give me -1/3, right? What is that number? Or better yet, how about this? How about I say, if this is 2/3, okay, if I factor out a total x plus 2 to the first power, really effectively what it's going to do is it's going to subtract 1 from this power. So look, this becomes x plus 2 to the -1/3 power times 3x plus 4 times x plus 2 raised to the 2/3 minus what I took out, 1/3.
Let me see what you guys are saying here. Okay, take 2. Sonia was talking. Okay. All right. Take a deep breath, everyone. So the way you do this is when you see this problem right away, you see which one of the common terms, this x plus 2, has the lowest power. It's this negative guy. Okay. How do we factor this out? Well, we pull it out from here, and all that remains is this 3x. So what does it mean to pull out
x plus 2 to the negative 1/3 power from here? Well, it means to take, if I were to multiply this x plus 2 to the negative 1/3 power times this term, it should restore it back to the 2/3. So x plus 2 to the negative 1/3 power times 4 times x plus 2, hopefully raised to the 1/3 power. What does this give us? Actually, this needs to be, I want to restore 2/3, right? So this needs to be to the 3/3, okay? Because when you subtract 1 from 3, you get 2, and that's what we wanted, right? So actually, I want this to be 3/3, okay? So notice that when I multiply x plus 2 to the negative 1/3 times the quantity 4 times x plus 2 to the 3/3, what you get is 4 times x plus 2 raised to the 3/3 plus, well, in this case, it's a negative, so it's minus 1/3. And notice that this reduces to what you had earlier. This is what you had earlier, right? Before you factored it. So I know what you guys are wondering. How did you know that this turns into a 3/3? Well, you know it turns into a 3/3 because if I were to put this back in, what number would this have to be if I were to add a negative 1/3 to it for it to go back to 2/3? That number is 3, because only 3 minus 1 gives you a 2. So that's how you do this part. And notice that 3/3 is just 1. So this factors into this. And then notice that when we get to this step, I can put that 4 through there. So I get x plus 2 raised to the negative 1/3 times this 3x plus 4x plus 8. And then this becomes x plus 2 raised to the negative 1/3 power. And now we combine these like terms. This 3x and that 4x gives me 7x plus 8. And so we're done. We've completely factored it as a product of two binomials. Okay. Any questions? Or do you guys want another example? Another example, yes or no? Do another example, please. Okay, another example. Everybody wants another example. Okay, so let's invent one. Let's do x times x plus 1 to the negative 2/7 power plus 2 times x plus 1 raised to the 1/7 power. Factor that. Okay. So again, what we want to do is we want to factor out the one that has the smallest exponent, and that's the negative 2/7. So what we get is x plus 2 times to be determined. It's going to be x plus 1, but its power is going to be to be determined. Okay. So notice that when I multiply x plus 1 to the negative 2/3 times another x plus 1 to a power, the exponents add. And we want it to be to where when I add a negative 2/7 to something over here, I restore a 1/7. Here's what I'm saying. 2/7 plus question mark gives me 1/7. 2 over 7 plus question mark gives me 1 over 7. Three. So it's got to be 3 over 7, right? Remember, 3 technically has 1 in the denominator, right? So it has to have 7 in the denominator. So it needs to be 3 over 7. Because look, negative 2 over 7 plus 3 over 7 is the same thing as negative 2 plus 3 all over 7, which then equals 1 over 7. Okay, so that question mark is 3 over 7. So this becomes 3 over 7. And in terms of this problem that I just invented just now, there's nothing else to factor. So, boom, you're done. This just has an x, this has a 2, and this quantity. There's nothing else to factor, so you're done. Does that make sense? Do you guys want one more problem? Absolutely. Oh, good. Wow, did you get the 3? Do you mean how did you get the 3? Okay. I got the 3, so I have negative 2 over 7. This 3 comes from here. We get the 3 because negative 2 over 7 has to add by something to get 1 over 7. Because when I factor out this quantity, I have to then multiply it back in by something to get it to restore to 1 over 7. Because remember, x to the m times x to the n is equal to x to the m plus n. Now, it's okay if this stuff doesn't sink in right away. This is the kind of stuff that I'm going to talk about in lecture, and you're going to have to go home and practice. If it doesn't make sense right now, that's perfectly fine. 100% perfectly fine. This is something you need to go practice. You need to sit in a dark room all alone with a lamp, you and your book, no one around, and just do the math all day, every day. Sounds menacing. No, it's what I do every day in my life. Am I menacing? What are you trying to say? I'm just kidding. All right, I'm gonna have to move on, but you're gonna have to math Zen, correct? This is just something that's gonna have to be practiced. Your textbook has a lot of practice problems, and your homework has a lot of practice problems. It's not supposed to all click during the lecture. It's supposed to click after you work on it. So it's okay if it doesn't make sense right now. But this is the key step. And this is what's going on here. I'll say one more piece before I move on. X plus 1 to the negative 2 over 7 multiplied by x plus 1 to the 3 over 7 is the same thing as x plus 1 to the negative 2 over 7 plus 3 over 7. And so that's why it equals x plus 1 to the positive 1 over 7. This is the key. Why am I talking about this? It's because this is what happens when you redistribute what you factored. So if you redistribute what you factored, you're supposed to restore what you originally had. And this is the term we originally had here. So this is something, it's going to require practice. And I have to move on to get to the other material. But if you have any questions, let me know, email me and whatnot. It's okay if it doesn't make sense right away. Mathematics is the most important and the most difficult subject invented by humanity. So if it doesn't make sense, don't feel bad. Some of the most brightest minds of all of humanity had difficulty with mathematics. Mathematics is the hardest, most complicated,
most intricate subject ever invented by human beings. And that's why it's so awesome, because it's hard. And hard and confusing stuff is fun. The harder and more confusing it is, the funner it is. It wouldn't be fun if it was easy, right?
What's the fun in that? What's the fun in something being really easy? You want it to be difficult. You want it to be challenging, so that when you do actually master it, you feel a sense of
Gratification and reward. 2.1, rectangular coordinate system.
all this means is, if we have an x-axis, we have a y-axis, I can define any point on the two-dimensional surface right here by saying, what is its value in x, and what is its value in y? For example, 1, 2, 3, 1, 2, 3, and 1, 2, 3, 4, 1, 2, 3, 4. The way I can describe this point in space is to assign it an x value, a 3, and to assign a y value, let's say a 4. So this point in space is quantified by a pair of numbers, 3 and 4. What if I put this down here? Well, 1, 2, 3, negative, the negative versions, and 1, 2, negative 1, negative 2. Now I can describe this as negative 3, comma negative 2, because now it's located here.
So rectangular coordinates allows us to be able to express the location of any point on two-dimensional space. It's typically called the Cartesian coordinate system, dedicated to the French mathematician René Descartes, because one day he was looking at a wall and he saw a bug on the wall, and he thought to himself, I can define the location of that bug on the wall by saying how high vertically is it from the ground and how far horizontally is it from the pillar or the wall. Those two lengths, those two pieces of information is all I need to locate the bug. So this horizontal axis is typically called the x-axis. This vertical axis is called the y-axis. Okay, so y is vertical, x is horizontal. Okay. Wonderful, wonderful, wonderful. Let's talk about how to graph. Okay. Given an xy, we can form a graph, something like this, where we call this thing our f of x. It's a function of x. A function is a mathematical expression such that when you put a number into it, it spits a number out. Matter of fact, we were talking about polynomials earlier. Polynomials are functions. For example, f of x is equal to x squared plus x minus 1. This is a function because if I give it a number, it'll eat the number. Let's say I give it the number 2. F of 2 is when this function is about to eat 2.
So for every x I see, I put a 2. So once f of x is equal to x squared plus x minus 1, each 2, what does it spit out? Well, it spits out what this computation will give us. 2 squared is 4. We add that to 2 and we subtract the 1. This gives me 6 minus 1, which is 5. So it took in a 2 and it spit out a 5. Okay? If I give it another number to eat, it will spit out another result. Okay? So whenever you plot these things, you get a table. Okay? Where's my eraser at? Okay, so here's going to be my graph. I'll set it up. Here's the x, and here's the y. Typically, x is called the x or the domain or the input. All of those are valid. Y is called the range or the output. Okay, so now, given that f of x is equal to x squared, graph 8. The way we figure out what the graph of a function looks like is we take something called an f of x table. And if you all excuse me, I will have to take a really short break here. Back. Got a candle lit. Oh, okay. Well. What? Okay. Now, let's try graphing f of x is equal to x squared. All right. What you create is something called an f of x table. The x is the input. The f of x, which is equal to our y, is the output. So what we like to do is pick symmetrical values about the origin. Let's say -2, -1, 0, 1, and 2. Let's pick -1, -2, -1, 0, 1, 2 as our inputs. -2, -1, 0, 1, 2. Can everybody see down there? Okay, everybody can see that, right? Okay. Okay. So now, what is f of x going to be? F of x is going to be f of -2. But what is f of -2? Remember, f of -2 is what happens when I replace the expressions in x with what's in these parentheses, which is a -2. And then I can figure out what f of -2 equals by performing the operation given by the function. The operation given by the function says take the input and square it, and the result is your output. So what is the output of -2 squared? 4. Yes. 4. So I put a 4 here. Now let's find f of -1. The function is f of x is equal to x squared. So f of -1 is -1 squared. And what is -1 squared? That's right, 1. So I put a 1 here. F of 0, what is f of 0? The function is f of x is equal to x squared. So f of 0 is 0 squared. And we all know 0 times itself is 0. What is f of 1? Well, the function says that's just 1 squared, which is 1 times 1, which is 1. What is f of 2? The function says that's just 2 squared, which is 2 times 2, which is 4. Okay. So we've listed some outputs for our desired inputs. Okay, so the next step here, let me no, that's actually a good spot for it. Now, here's what you do next. You find, now it's time to graph, okay? You find the location in x, -2, okay, we're here. Then you find what is the output of -2. We look on our table, we've tabulated that it equals 4. So I go to -2, then on the y, I travel 4 places up, 1, 2, 3, 4. On x, I'm at -2. On y, I'm at 4. I put a dot. Let's move on to the next input. -1, I'm over here. On the x, it's -1. The output for -1, f of -1 is 1. So I go to 1, 1, I put a dot. I go to 0 on x. The output of x at 0 is 0. I put a dot. I go to 1 on x. The output at 1 on x is a 1. I put a dot. Well, guess what we're going to do for 2? We go to 2 on x. We see the output of 2 is 4. What do you think we're going to put right here? Someone tell me. We're going to put a dot. A dot. Spell it like I'm saying it. Gonna put a dot. Someone spell it out. Yeah. Yeah. That's right. D-A-A-H-H-T. Yeah, that's right. A dot. So this one is kind of a little high here. Okay. So once we're done putting in our dots, okay, guess what we're going to do to the dots? We are going to connect the dots. So look. Once we connected the dots, and I know what you're thinking, well, there was no dots to connect up here. Fine. Fine, here you go. Don't even do that. We just connect the dots, okay? But if you were to pick -3 and -4 and -5 and find their outputs, you'd realize that it indeed does look like that. Okay? So we just graphed our first function together. This function right here, this is f of x squared. And you better get used to this function. This is a very important function in math. We talk about it all the time. F of x is equal to x squared. This shape is what we call a parabola. Every time you see a shape like this, we call it a parabola.
Okay. Let's graph another function.
Let's say f of x is equal to negative x plus 2. We're going to create an f of x table. And we're going to create a new graph. Here's my x, here's my y. We're going to pick some values about the origin. Negative 2, negative 1, 0, 1, 2.
Those are some good values to pick.
They're always good because it's a little bit to the left of the origin, a little bit to the right of the origin. We can get an overall kind of good picture of what's going on. So our input will be negative 2, negative 1, 0, 1, 2. So now we just have to determine what is f of negative 2. Go to our function. Replace every x you see with a negative 2 and compute the result. Well, f of negative 2 is negative negative 2 plus 2. That's positive 2 plus 2, which is 4. So I put a 4 right here. What is f of negative 1? We go to f of negative 1. That's negative negative 1 plus 2. That's 1 plus 2, which is 3. So I put a 3 here. What is f of 0? F of 0 is just negative 0 plus a 2, which is just 0 plus a 2, which is 2. So I put a 2 here. Guess what we're going to do here? This is going to be f of 1. So I put a negative 1 here plus a 2. What is negative 1 plus a 2? That's positive 1. What is f of 2? Well, that's negative 2 plus a 2. Negative 2 plus a 2, that's 0.
Right? Any objections? A doubt. A doubt. A doubt. A doubt. No objections. Okay, so what do you guys think I'm going to do? I'm going to go to negative 2 on the x. What am I going to, I'm going to go to 4 on the y. 1, 2, 3, 4. 1, 2, 3, 4. What do you think I'm going to put right here? At negative 2 on x, I'm going to travel up to positive 4 on y. What do you think I'm going to put here? A dot.
Very good. Then I go to negative 1. I see a positive 3. Okay, I'm a negative 1 here. I go 1, 2, 3. What am I going to put here? A dot. I go to 0. I see 0 outputs 2 on the y. So I go at 0, 1, 2. I put a dot. I go to 1. I see 1 outputs a 1 on the y-axis. So I put a dot. And I see 2 outputs a 0. I go to 2. Y is 0. I put a dot. And guess what we do once we put all the dots? What are we going to do to the dots to find the graph?
Draw a link. Connect them.
Yes. Boom. There's our graph. And if you were to graph infinite number of points to the left and infinite number of points to the right, you'll see that it just forms a line like this.
So that's how you graph functions. whatever your function is, you create an f of x table, you play this game, and this is how you graph stuff. Okay? So, this function equaled f of x is equal to negative x plus 2, right? Or was it plus 1? Yeah, it was plus 2. I can tell by looking at the graph, because the output of 0 is 2. So it had to be negative x plus 2. So now, what is the x-intercept? What is the y-intercept of this graph? So what does x-intercept and y-intercept even mean? Well, it literally means what it sounds like. It's where the x-intercept is where it's touching the x-axis. So this is the x-int. And the y-intercept is where it's touching the y-axis. This is the y-int. So by visual inspection, because we've already graphed it, we know that the x-intercept is at 2, 0. Because we have to say, oh, it has value 2 on x and value 0 on y. And the y-intercept here has value 0, 2. Because it has no x, but it has 2y. Okay? So we've answered these questions here. But what if we hadn't graphed the function? What if I have f of x is equal to negative 3x plus 4? What is its y-intercept? What is its x-intercept? Do I need to laboriously graph things to find their intercepts? We all know that graphing things like this, creating a table, putting dots, connecting dots, that kind of takes time, doesn't it? Kind of takes energy and it takes time. Notice that we can figure out what the x-intercept and the y-intercept is algebraically. Drawing a random picture again, notice that the y-intercept implies x is equal to 0. And notice here, the x-intercept implies y is equal to 0. All we have to do is, given our function right here, if we wish to find its x and y intercepts, we just have to adhere to this logical conclusion that the y-intercept has x value 0. So let's find the y-intercept for this function. So if this function has x value 0, then f of x, which, note, f of x is equal to y, is equal to negative 3 times 0 plus 4. Because we're trying to find the y-intercept. Okay? So negative 3 times 0 is 0 plus 4. It's a 4. This implies y is equal to 4. So then we can say that the y-intercept of this function right here, it must be at 0, 4. We didn't even have to graph it. Where is its x-intercept? Logically, when a function crosses the x-axis, its y value is set equal to 0. So we can set f of x, which is equal to y, equal to 0, which is equal to negative 3x plus r4. So notice now we can solve for x. Just subtract the 4 from both sides. I get negative 4 is equal to negative 3x. And then x is equal to, divide both sides by negative 3, positive 4/3. So this location right here
is at 4/3, comma 0. That's where the x-intercept is. So y-intercept ends up equaling 0, comma 4. X-intercept ends up equaling 4/3, comma 0.
And unfortunately, we are out of time. I'm actually almost 5 minutes over.
So our goal was to get to 2.2 and 2.4, but we were only able to do this much.
And let's see how much of 2.1 have we even gotten through. Not a whole lot, okay? So what I'll do is
You all will be responsible for this. 1.3, 1.4, and 1.5
is what will be due in a week from today, okay?
So I'll extend the due dates. I'll extend the due dates for 2.1, 2.2, and 2.4.
I'll extend those due dates until we can cover them next class period. Yes. Yeah, sometimes, especially during the early sections, I tend to go a little slower. That's because I want everybody to understand stuff really, really well. The basics are the most important. If you have a good mastery on the first subjects, on the first chapters, you will understand the rest of the chapters, or you have the opportunity and the skill set to be able to handle the rest of the work. If you don't understand the stuff at the beginning, if you don't spend the time to work on it yourselves and to master it, well, it's only going to get worse, because we're going to be talking about stuff that just builds upon these ideas, like, you know,
X to the m times x to the n equaling x to the m plus n.
That's going to be used over and over and over again.
The fact that the square root of x over y is the same thing as the square root of x over square root of y,
that will be used over and over again. All these things that we talked about on the first day and the second day of class, they will be coming up over and over again. So you guys need to work very, very hard. Work very, very hard now, so that when the tail end of the semester comes, you are much more equipped to perform well on your assignments and on your tests. Right now, you should be treating right now like it's finals week, you know? Grind now like it's finals week. So when finals week comes by, it's much easier on you. And math sometimes takes a while to absorb. And so just because it doesn't make sense now, doesn't mean it won't make sense later on. You need to go and work at it, you know? Mathematics is like learning how to ride a bicycle or learning how to play a musical instrument. Nobody pops out the womb playing the Bach chaconne on the violin, okay? That's just not possible. So mathematics is intrinsically, inherently complicated. And because it's complicated, it can be seemingly difficult. But that's not how we think. Most people think, oh, if it's complicated, I don't like it. If it's complicated, I'm intimidated by it. I want you guys to reframe the way that you think. I want your mentality to be that, oh, the more complicated it is, the more fun it is, right? Because when you know, what do you young kids do? Y'all play video games? What happens when you beat the first level? The second level gets harder. The third level gets harder. The fourth level gets harder. Why does it get harder? Because if it gets easier, then the game's boring, right? It's gotta get harder and harder for the game to keep you interested. And that's why mathematics does that. The modern day mathematics is levels above this stuff, and it's really awesome, but it's built off of these foundations. This mathematics was created thousands of years ago, and now we have modern day mathematics that's built off of these very foundations. So if you guys work really hard and understand this stuff, not only will you pass this class, but maybe down the line, if you so desire, you could continue your study of mathematics. Awesome. Thank you. Thank you so much. Thank you for explaining the fractions as much as you could. Gonna go practice section for sure. Yes. Yeah, it's okay if it doesn't make sense right away. You got to go and do it on your own. Mathematics is not a spectator sport. It's not a sport at all. But you can get mathletic. And the way to get mathletic is to do mathematics. I suggest doing supersets, meaning back to back, just keep doing it nonstop until you can. Do math until you puke. Thank you so much for explaining fractions. I'm absolute, no. Okay? Definitely practicing, I like that, okay? It's okay to tell yourself, hey, right now, I'm not good at this. But then you have to then do what you're saying and say, definitely practicing, meaning I recognize this is a weakness and I'm going to work on that weakness. Because why? I'm able to grow. Growth is a possibility. And the harder you work, the more you can grow. And that's just the truth in life. That's just the truth in life with everything. The harder you work, the faster you can grow. So if you recognize you have a weakness somewhere, work on it. Work on it. Don't give up. It might be hard, but if you don't give up and you keep trying, you will improve. Now, here's the thing. You have to analyze how you work. Sometimes you have to work smarter and not harder. Okay? Other times you do have to work harder. You have to analyze whether the way you're attempting to solve a problem is useful. Sometimes you can attempt to solve a problem and you try it one way, and then you try it the same way, then you try it the same way. So you have to then analyze, how am I going about this? Maybe I need to change the way I approach the problem. That's one step to getting better. One step to improvement is to analyze your mistakes and to critique them and to improve them. Another way to get better that's independent of that way is more effort. If you put in 2 hours to studying for a test and you get a D, double that, put in 4 hours. Maybe you might then get a C. Double that, put in 8 hours, then maybe you might get a B. Double that, put in 16, maybe you might get a B plus. Double that, you get 32, maybe you might get an A minus. Double that, put in whatever doubling that is, 64. That's how I think about it. I do a two-step way. If I don't get what I want, I double my efforts and I analyze how I'm approaching it. So not only am I increasing my efforts, but I'm also increasing my approach. I'm making my approach more efficient by analyzing my past mistakes. That step is very important because anybody can just dump more and more effort in. But sadly, if you just dump more and more effort in and you don't have any internal reflection on, am I doing this the right way? Is there a better way? Should I think of a different way of approaching this? You will be disappointed because you'll put in a lot of effort and get very little result. So it's not about just doubling, tripling, quadrupling the amount of time you put into something, but it's also about analyzing the way in which you're doing it, making it more efficient. Thank you so much for explaining fractions. If I go back to my previous homework, can I continue to practice on there, or do they lock? To be honest with you, Carrie, I don't know. You need to check and let me know. And if they lock, I'll try my best to get it unlocked if it's possible. I'll have to talk to my colleagues about that, about the possibility of doing that. It should be possible. So I just checked and it lets me. Well, there you go. There you go. Thank you. Just checking this. They don't lock. Well, there you go. Now we know. You're very welcome. Okay. Any other questions? Have a good night. Gotta eat dinner. Absolutely. I am starving. I'm starving. Okay, good night. Any other questions? No, but I'll be practicing. Have a good night. That's the right attitude. That's the right attitude. If it doesn't make sense, you're gonna work. If it doesn't make sense, then you're gonna work more. If it doesn't make sense, then you're gonna work more and analyze yourself. Try and improve the way you're trying it and work more. Trust me, if you keep doing that in a step-by-step way, success is almost guaranteed. You're almost guaranteed to be successful if you never give up, constantly double, quadruple, octuple your efforts and analyze your mistakes. You're bound to succeed in anything. All right. Seems like nobody has any questions. Where can I find the recorded classes? I upload them on my YouTube channel, and I also upload them on Canvas. I prefer if you watch it on YouTube and like it and subscribe to my channel and share it on social media to all your friends and whatnot. That would be great. I'm trying to get my followers up and whatnot. But you're not forced to do that. So you can look at it on Canvas or you can look at it on YouTube. My YouTube channel, I can write out the name. It's called and I have not only our recorded lectures on there, but I have videos on how to do a lot of I have all of pre-calc. I have all of your class on there. On how to do everything in this class is on my YouTube channel. Factoring is on my YouTube channel. F of X, X table, and how to graph is on my YouTube channel. So you have that as a resource as well. You can ask questions on the videos by leaving them in the comments on YouTube. You can ask questions on this chat. You can ask questions via email. Okay. Seems like nobody has a question. Without further ado, I'll see you guys in a week. Work hard.